The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI Web Sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
At this time, I'd like to introduce our next speaker, James Donnelly, Deck Condition Assessment using Non-Destructive Testing Methods.
Good morning. Thank you all for coming. I have what I think is a fairly interesting case study that I want to present today. And I'm going to start out talking. It's a case study involving condition assessment of bridge deck. In and of itself, that doesn't sound very exciting. But during this case study, what we did was we actually used 5 different non-destructive testing methods, tested the same areas, and tried to get a sense of which of these techniques were the most beneficial, most helpful in terms of getting good results for delamination assessment. Before I go any further, I want to make sure I thank my 5 other co-authors from WJE who did a lot of the hard work in data gathering and data reduction for this. I also want to thank our contact from the Iowa DOT, who was the driving force behind this study. Briefly talk about an outline of the presentation I'm going to give today. I want to start out with a little bit talking about the background and the motivation behind the study. Then I'm planning on getting into the evaluation approach with each of these different techniques. And then really get into the meat of the presentation, which is the findings. Which one of these techniques worked well and what were their shortcomings and advantages. And then kind of wrap it all up with some conclusions, some brief conclusions at the end. All right, so background, motivation. What's the motivation behind this? What's driving this? Well, a typical state DOT in the United States, or a provincial DOT here in Canada, is responsible for hundreds of bridge decks. The repair and maintenance of those things. How do they keep track of that inventory? How do they know where they need to spend their dollars? They all have limited amounts of money that they have to spend to keep the bridge decks in the best possible conditions. So it's important for them to be able to do condition assessments of bridge decks on a fairly regular and quick basis. So DOTs are looking for rapid, inexpensive, and accurate techniques for doing these assessments. The particular bridge deck selected for this study is somewhat interesting. It's built in 1976. Takes Interstate I-129 over the Missouri River. Just outside of Sioux City. Now, I didn't even know that there was an Interstate I-129 when I started this work. It's a fairly short section of highway connecting I-29 in Iowa with just south of Sioux City, Iowa, with Sioux City, Nebraska, which is just right across the river. So it's only a few miles long. The bridge deck itself is an 8-inch bridge deck with conventional reinforcing, uncoated bar. Prior to opening the bridge to service, a 2-inch thick Iowa low slump concrete overlay was cast over the deck. I think the thought process behind that was basically a sacrificial overlay, if you will, sacrificial wearing surface perhaps, that can provide protection for the main bridge deck. It's a fairly long structure, approximately half a mile long. There's 2 expansion joints that divide the structure into 3 segments. There's basically an east approach, an expansion joint on the east bank of the river, main spans over the river, another expansion joint on the west bank, and then the west approach spans beyond that. The bridge deck, maybe can't see from this photograph, was in pretty good condition when we got there. There was localized concrete repairs at a few locations, and the Iowa DOT had recently performed some epoxy injection of the delaminations within the bridge deck. All right, evaluation approach. How do we go about doing this? Well, First thing we did was we did a visual and a sounding survey of the entire bridge, all 2,600 feet, and it's actually 5,200 feet because there's actually two different structures for the eastbound and the westbound lanes. Within those areas, based on the data that we got, we selected 6 study areas, one in each section between expansion joints, in both the eastbound and in the westbound lanes. And generally what we tried to do was we tried to pick locations where we had a fair amount of delamination, where we had some of that epoxy injection repairs, some previous repairs perhaps, so that we could get maybe the most variables thrown at these different types of non-destructive testing systems. We used coring to confirm delaminations at a number of locations. Obviously, we couldn't core the entire deck, but we picked locations where we thought we had delaminations or where something peculiar was showed up in one of the NDT testing techniques that we wanted to find out, was it a delamination or was it not? And of course, we did the delamination assessment using these 5 different condition assessment techniques. What were these techniques? Well, we used the typical chain drag sounding type technique. We also used infrared thermography, ground penetrating radar, impact echo, and half cell potential testing. In this picture here, you can actually see one of our study areas. We had the 6 study areas. Each of them was 200 feet long and basically were the width of one travel lane and the adjacent shoulder. So it's basically a 20 to 24 4-foot wide width of the bridge deck we could test within those sections. Chain drag sounding, pretty simple stuff. There is an ASTM for it, believe it or not. But you're basically listening for changes in the tone of the chain as it's dragged across the concrete surface, because a delaminated concrete will produce a higher tone than if you're going over sound concrete surface. So you can get somebody who's fairly lowly skilled but has a good ear to do this type of work. Oh, that's a picture of me there, sorry. Any case, so pretty simple, straightforward stuff to do. Infrared thermography. What does infrared thermography consist of? How did we do it? We basically took a large van, a Sprinter type van, and mounted a frame onto the back of it, and we had an optical camera and an IR camera right next to each other, photographing or taking pictures of the same surface continually as the van basically was rolling forward across the bridge deck. How this system works is basically you're looking for small thermal differences in the concrete surface. Delaminated concrete is going to heat up and cool down faster than the main portion of the bridge deck, because you just don't have that same level of mass. You've got basically an insulating, that delamination plane, if you will, is basically an insulating layer, if you will, from the rest of the concrete. So those surfaces pick up. So in the morning, the deck will be heating up faster. You can find delaminations by looking for hot spots. In the evening, when the sun goes down, the delaminations will cool faster. But you're looking for small thermal differences. All right, ground penetrating radar. How does the ground penetrating radar work? We're basically sending a radar signal into the concrete deck. The radar signal is going to bounce off a reinforcing steel. So it's very effective at finding reinforcing steel. In terms of delamination detection, you're kind of actually finding delaminations indirectly. How you're doing this is you're basically relying on the fact that certain features that are affected with corrosion of the rebar within the concrete deck, such as locally elevated moisture contents, chloride contents, or corrosion byproducts, those are going to attenuate or affect the reflection signal coming from the reinforcing bar. So you look for that attenuation in the response data, and you can infer from that that there may well be a delamination in that area. Impact echo. This is actually a device. There's actually more to this than just a hood over what looks like a radio flyer wagon. It's actually a fairly highly sophisticated device, but that's actually computer equipment back there that's covered because it was starting to rain at the time this photograph was taken. But the impactors, there's 2 wheels with impactors on here. And basically, as this device is rolled across the surface, those impactors impact the surface. It excites the surface of the concrete, and they basically read the resultant echo coming from the concrete. So you can find delaminations anywhere that they might occur within the bridge deck, because it's basically the sound wave is going to go into the concrete and bounce off of whatever it can bounce off of. If it's the bottom of the deck, it's the bottom of the deck, and the signal takes so long to get back. If it's the top layer reinforcing steel where the delamination plane is, the signal will come back a lot faster at a different resonant frequency. Half-cell potential testing. Half-cell potential testing, Stephen talked about this a little bit in his presentation. You're basically measuring the electric potential difference between the half-cell, which has a known potential, and the reinforcing steel. And the concept in this case is as Stephen stated, those locations with more negative readings are more likely to be having corrosion. So this also is kind of an indirect measurement of delamination. It'll tell you where you have a corrosion potential if you have an idea where corrosion may be occurring. And those are the locations we know where delaminations may occur. So we're using this one to, again, indirectly determine where there may be delamination. All right, so what kind of information did we come up with? Well, the chain drag survey, we went through, found cracks, delaminations, found the surface defects. We recorded locations where injection ports were located from the epoxy work that the DOT had performed. Then we compared those findings to our cores. And based on this information, the delamination survey was essentially 93% accurate. There's 2 locations where the cores found a delamination lower in the deck that the delamination survey didn't find. So because this is a fairly high accuracy level, this basically became the basis that we compared the other techniques to. In other words, did these other techniques find those same delaminations that the chain drag surveys found? Now, a few words of warning about this thing. It's obviously going to be user dependent. Everybody has a slightly different ability to recognize tone. One of my associates, one of the co-authors, suggested maybe we should have had a group of music students come out and do the chain drag survey for us, because they would have the best tonal sense. We did not do that. But obviously, you don't want to send somebody who's tone deaf out there because you might not find any delaminations. But then there's things that can interrupt the sound for the user. Traffic volume. For example, if there's trucks driving by us on this operating bridge deck, you may miss delamination in those locations. Environmental factors. There was one day we were out there, the wind was blowing at 30 miles an hour on average. Now I can tell you, if I could keep my hard hat on, and it was screwed on pretty tight that day, giving me a headache pretty quickly. But if the wind with blowing by can affect the ability to hear sounds, particularly the higher tones that you might be looking for shallower delaminations. So those are issues in terms of the accuracy. From a DOT's perspective, they don't really like them because you have to lane closure. It's fairly labor intensive and it's not that fast. But because it was pretty accurate, that was what we used as the basis for the comparison portion of this study. Infrared thermography. The intent behind the data shown here is basically showing that some locations we got pretty good confirmation, and some locations we had places where they didn't quite match up. But the infrared thermography did a pretty good job of identifying delaminations. We found a lot of surface discolorations, the places where that epoxy had spilled on the surface from the epoxy injection work that the DOT had done. Those things heated up pretty quickly. We also were able to identify patches, particularly those that were debonded, because they obviously were heating up pretty quickly. In terms of evaluating the data, we found that the infrared thermography identified 30% of the areas we found delaminated by sounding accurately. But it also found 42% of what we're calling false positives. It's finding delaminations in areas we didn't find with sound. Now, at first reaction, this doesn't sound like this is very good, but actually, in terms of the false positives, this is actually a pretty good number compared to the other techniques we used. Quick look at the data. Obviously, the results can be affected by sun exposure, can be affected by time of day. You want to make sure the bridge deck is heating up. A little visual over here on the side basically shows one area. We've got epoxy on the surface. You can see how that heated up and shows as bright in the thermal imaging. And then we also had a delamination here marked by the delamination survey crew. And you can see that that's showing up. We're not getting the same limits, but there may have actually been some moisture in that delamination plane that hadn't dried out at the time that the survey was performed. So we were picking up surface discolorations. The depth of the delamination can play a factor. Again, think about this. You're looking for small thermal differences. If the delamination is much thicker, the thermal difference to the rest of the concrete is not going to be as great as for smaller delaminations. In terms of performing the work, it's fairly simple to actually go out and do the data once you collect the data, I should say, once you have all the equipment set up in the right settings. But interpretation is going to require some experience because you're going to have to look for stuff like this where there's epoxy on the surface. If you were to the untrained eye, you might think this is a delamination, which also does bring up a possible issue for why there might be errors in this system on this particular bridge deck, because that epoxy injection, it may be masking an actual delamination in that location that the infrared thermography would imply that there is, but the guy who's evaluating the data might say, well, no, that's epoxy on the surface, that's why that's hot. There still could be a delamination underneath that epoxy. All right. Ground penetrating radar. Ground penetrating radar, it did have some success identifying delaminations. It's worked great in terms of identifying the rebar locations and the spacing and the cover. We use two different antennas for the GPR equipment. We use a 2.6 gigahertz antenna, and we also use the 1.6 gigahertz antenna. Of the two, the 2.6 seemed to be more accurate. It correctly identified 29% of the delaminated area as compared to what was identified by the sounding technique, and fairly high amount of false positives, 92% of the size of the lamination area, where it thought that something might be delaminated that wasn't yet. It helps to understand how this system works, to know why you might get the results that we got. Here's a little bit of here's a sample of some of the data from the project. You can see in these locations, in between these areas here, you got fairly bright, sharp imaging of where the reinforcing bars are. And each one of those parabolic curves at the top of that peak is where the reinforcing bar is located using the GPR. This is pretty typical standard stuff that you would get out of a GPR test. But notice there's some areas here where it's not all that sharp. It's kind of a little bit fuzzy on the screen. Well, that's where that signal is being attenuated by the moisture in the deck, by possible corrosion byproducts, by chloride ions in the concrete. So those are the locations that we were taking to be inferring as potential delaminations. So again, maybe you have all that stuff, but the delamination hasn't occurred yet, and that may explain why maybe that number is a little bit higher in terms of the false positives. In terms of the accuracy, you can see how the interpretation of the results is going to require some experience to make sure that you're getting good results. The actual collection of the data is basically a fairly simple device that's being carried over, driven, dragged, pulled across the concrete surface. So it doesn't require extensive field user qualifications, let's put it that way. So the accuracy is fairly field user independent. But it will require lane closures. Now you can get this equipment. There is some stuff where it's been like mounted on a trailer and stuff like that. So maybe you could even handle it with a rolling lane closure. But it's not incredibly user intensive in terms of performing this work. All right, impact echo. The impact echo stuff was very good at identifying top and bottom delamination surveys. The percent that correctly identified from the delamination survey, this is the highest of the four non-sounding techniques that we used. 69% of the delaminated area correctly identified. It did have a fairly high number of false positive, 94% the size of the laminated area. So that's a little bit disconcerting, but in terms of the overall projection, you can see it's fairly accurate. The impact echo. So what do we know about the impact echo, and what do we learn in terms of techniques? It's providing data regarding top and bottom surfaces. Now, the stuff on the previous page, we did try to rule out the bottom surface delaminations because obviously the other techniques, we're not going to be picking that up. In terms of getting this equipment across the surface, by the way, I should mention the fact that Olson Engineering actually did this portion of the study. They actually did the field data collection and provided us with their report as a part of our study. Any case, accuracy is basically field user independent once you have the equipment out there and it's properly set up. If you're using equipment like this, it is going to require lane closures. They do have stuff that can be mounted on the back of a pickup truck, for example. So maybe you could handle it with a moving lane closure, but it would not be a very fast moving lane closure. You may have to double back over areas because you're only getting maybe a 6 or 8 foot wide strip in those particular instances. Half cell potential testing. How does the half cell potential testing work? How was it going? Obviously, half-cell potential testing, you're finding areas where you're actually likely to have corrosion. So is it delaminated or not? Well, maybe, maybe not. We found that approximately 44% of the areas where we had high potential, electrical potentials, basically corresponded with delaminated areas. So 44% success rate, if you will, which isn't bad. It's not as good as a couple of the others. It did have a huge number of false positives as compared to sound areas that had high negative readings. And if you think about how that testing technique works, those may be locations where maybe corrosion may have occurred, but the delamination hasn't started yet, or maybe where you just have the electrical potential for corrosion to occur, but the actual corrosion process hasn't started. So I think that explains why that number is fairly high. But again, so it's providing data regarding the corrosion state of embedded reinforcing. In terms of what needs to be repaired right now from the DOT perspective, that's not going to tell you exactly what that quantity needs to be, but it will give you a good handle on what may need to be addressed in the future. How much is corroding right now? Do we have a problem down the way that we need to keep a closer eye on this particular bridge deck? In terms of disadvantages, it does require drilling into the deck to expose the reinforcing steel. You have to do that at regular spaces, depending on what kind of continuity you have within the reinforcing steel within the bridge deck. The guy's doing out in the field, he needs to know what he's doing. He needs to know if he's getting good reading. In this particular case, we used a kind of an interesting system where we basically had multiple half cells set up on this one, for lack of a better phrase, rig, where you basically could, it's kind of like a glorified luggage cart, if you will. You could basically roll it down, 2 feet, set the thing down, let the readings stabilize. We had a data recorder there, basically record the readings, and then basically we back the thing back up and then move it forward another 2 feet and take another reading. So in terms of interpretation, the user, it helps to know how you're using the equipment, helps to have some experience there, and also helps to have some experience in terms of evaluating the results. So in terms of conclusions, what we found out was that in this particular bridge deck, the impact echo was found the most correctly identified the most locations in terms of the 4 NDT systems, not including the sounding. Infrared thermography was also pretty good because it had the fewest missed the false identifications, i.e. it didn't have a lot of false positives. GPR was not quite as good, but it provided a lot of good, useful information in terms of reinforcing bars. How frequently spaced are they? How much cover do you have? Where are they located? Etc. Half-cell potential testing. I think we just kind of threw it in there thinking, it's an evaluation technique. I didn't have high hopes for it. It actually did better than I thought it was going to do. It definitely identifies areas where corrosion has occurred or is occurring or is likely to occur in the future. So that maybe is a good long-term number for the DOTs to have, even though it might not necessarily relate directly to the upcoming repair project that the DOT may be planning for at that moment in time. Of these different systems, infrared thermography is perhaps the only one that you can really do without a lane closure, although, you could basically have it mounted on a truck and moving along at 5 miles an hour. So it's a rolling lane closure. It's not ideal. A couple other systems have that potential. The GPR and the impact echo could also be done with that. The big hang-up on infrared thermography, though, it's really it's very sensitive to weather. If you don't have that sun, you're not going to get the deck heating up with differential thermal values at delaminations. On a rainy day, you're not going to be able to get anything valuable. We actually were out there, we had a couple days of rain when we were out there doing this survey, and we could do the impact echo. We could do the sounding where there wasn't standing water. We could even do the GPR if there was no standing water, but the half cell and the infrared thermography would basically be shut down on those days. So, and another important thing to point out is how accurate these are relative to the users. The various, is a different user going to come up with different results? The impact echo, the infrared thermography, and the ground penetrating radar are relatively independent of the user in the field, whereas the other, the sounding and the half cell are not quite as much so. Although I will again point out that all 3 of those techniques it does require a fair amount of data interpretation once the field work is completed. So at this point in time, I think I'll open it up to questions. Yes, sir. The question is regarding using the Schmidt hammer to impact the top surface. And we did not consider using the Schmidt hammer. I think the effect would be pretty similar to either what we're getting from the impact echo if you're reading the response, or the sounding survey, because yes, it's basically a combination of the two. So I guess we thought there was going to be too much overlap if we had tried to use that technique in this particular instance. Pericles?
Yes, I would like to follow up on the response that is feedback test, not very just for very good programs, has to use in fact is very well proven method. But my question is different right now, is that it's possible that when comparing the non-destructive methods, infrared, infrared, and GPR, and the sounding, apparently the sounding, the oldest method, is the best method, but actually may not be the best method for deeper delaminations.
Absolutely.
And that's why you have Delamination that identifies the deepest delaminations. And I'm wondering whether this 90% false delamination to get for infrared water because they are deeper and they couldn't really identify with the chain dragging. And also the infrared gets some responses for reinforcement or sometimes layers. That is not really a problem, but you separate those cases?
Well, we did try to separate out the stuff that was off the bottom, that we knew was off the bottom. Now, it was a little hard to do the visual survey of the bottom over the river, but where we were over the land, we could figure out where there was stuff on the bottom. There wasn't a lot of delaminations on the bottom. We could basically correlate that with what our impact echo stuff was. So I don't think that creates a great deal in terms of the impact. I think the epoxy and the surface played a role on that at those locations, because that was obviously giving a different reading back during using the impact echo. There may have also been some deeper delaminations that maybe we didn't find with the chain drag survey. Again, though, I would say that most everything that we found, we were able to confirm with coring in terms of the sounding survey. So there may well have been some deeper delaminations that maybe we didn't pick up, and that would explain maybe some of that percentage. If you think about it, with the sounding survey, you need a bigger metallic item that you're hitting the deck with to create that sounding if you're looking for deeper and deeper delaminations. A very thin chain is not going to pick up much more than an inch, inch and a half, 2 inch of delamination. So we're using a fairly heavy chain, so we should have been picking up everything, but the rebar with that 2-inch overlay, that rebar typically had 3.5 inch cover on the top deck, so top deck reinforcing. So that could be part of the role, yes. Okay, well, thank you very much.